Hello, and welcome. In this video, we will explore the crucial relationship between differentiability and continuity, a fundamental concept in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to state and prove the theorem that differentiability implies continuity, understand why the converse is not true, and use left-hand and right-hand derivatives to test for differentiability at a point. Let's begin by recalling the definitions of these two concepts. A function f is continuous at a point x equals a if the limit of f of x as x approaches a is equal to the function's value at a. Intuitively, this means you can draw the graph through that point without lifting your pen. A function f is differentiable at x equals a if the limit of the difference quotient exists. This limit, which we call the derivative f prime of a, represents the instantaneous rate of change or the gradient of the tangent line to the curve at that point. Now, let's investigate the connection between these two ideas. Our first objective is to prove a key theorem. If a function is differentiable at a point, then it must also be continuous at that point. Let's state this formally. If a function f is differentiable at x equals a, then f is also continuous at x equals a. To prove this, we need to show that the condition for continuity is met. That is, we need to show that the limit of f of x as x approaches a is equal to f of a. Let's start with the expression f of a plus h minus f of a. Our goal is to show that the limit of this expression as h approaches 0 is 0. We can manipulate this expression by multiplying and dividing by h. So f of a plus h minus f of a is equal to f of a plus h minus f of a, all divided by h, and then multiplied by h. Now let's take the limit of both sides as h approaches 0. The limit of the left side is the limit of f of a plus h minus f of a. The limit of the right side is the limit of the product we just created. Using the limit laws, we can split the limit of the product into the product of the limits, provided both limits exist. This gives us the limit of the difference quotient multiplied by the limit of h. We know that f is differentiable at a, which means the limit of the difference quotient exists and is equal to the derivative f prime of a. So the first limit is f prime of a. The second limit, the limit of h, as h approaches 0, is simply 0. Therefore, the product is 0. This means the limit of f of a plus h minus f of a is 0. We can rewrite this by adding f of a to both sides. This gives us the limit of f of a plus h as h approaches 0 is equal to f of a. Now, let's make a substitution. Let x equal a plus h. As h approaches 0, x approaches a. Substituting this into our equation, we get the limit of f of x as x approaches a is equal to f of a. This is precisely the definition of continuity at x equals a. And so, we have proven our theorem. If a function is differentiable at a point, it must be continuous at that point. This means that for a function to have a well-defined tangent line at a point, it cannot have any breaks, jumps, or holes there. Now that we've proven that differentiability implies continuity, let's consider the converse. Is it true that if a function is continuous at a point, it must also be differentiable at that point? The answer is no. The converse is not true. A function can be continuous at a point but not differentiable there. To show this, we need to find a counterexample, a function that is continuous but not differentiable at a specific point. The most famous and straightforward example is the absolute value function, f of x equals the absolute value of x, at the point x equals 0. Let's first confirm its continuity at x equals 0. The absolute value function is defined as x for x greater than or equal to 0, and negative x for x less than 0. The left-hand limit as x approaches 0 is the limit of negative x, which is 0. The right-hand limit is the limit of x, which is also 0. Since both one-sided limits are 0, the overall limit is 0. The function's value at 0 is the absolute value of 0, which is 0. Since the limit equals the function's value, f of x equals absolute value of x is continuous at x equals 0. Now, let's test for differentiability at x equals 0. To do this, we need to introduce the concept of left-hand and right-hand derivatives. The left-hand derivative, denoted f prime minus of a, is the limit of the difference quotient as h approaches 0 from the negative side. The right-hand derivative, f prime plus of a, is the limit as h approaches 0 from the positive side. A function is differentiable at a point if and only if both the left-hand and right-hand derivatives exist and are equal. Geometrically, this means the tangent line must have the same slope from both sides. Let's apply this to f of x equals absolute value of x at x equals 0. For the left-hand derivative, h is negative. So f of h is negative h. The limit becomes the limit of negative h over h, which is negative 1. For the right-hand derivative, h is positive. So f of h is h. The limit becomes the limit of h over h, which is 1. We see that the left-hand derivative is negative 1 and the right-hand derivative is 1. Since they are not equal, the function is not differentiable at x equals 0. Visually, the graph of y equals absolute value of x has a sharp corner, or a cusp, at the origin. You can't draw a single well-defined tangent line there. This sharp corner is the geometric reason for the lack of differentiability. So, we have successfully shown that a function can be continuous at a point but not differentiable there. This confirms that the converse of our theorem is false. Let's summarize the conditions for differentiability at a point x equals a. For a function f to be differentiable at x equals a, two conditions must be met. First, the function must be continuous at x equals a. Second, the left-hand derivative and the right-hand derivative must both exist and be equal. Let's work through an example to see how to apply these conditions. Consider the piecewise function f of x, which is x squared for x less than or equal to 1, and cx plus d for x greater than 1. We want to find the constants c and d that make this function differentiable at x equals 1. We must satisfy both conditions for differentiability. Let's start with continuity. For continuity at x equals 1, the left-hand limit, the right-hand limit, and the function's value must all be equal. The left-hand limit is the limit of x squared, which is 1. The right-hand limit is the limit of cx plus d, which is c plus d. The function's value at 1 is 1 squared, which is 1. Setting these equal gives us our first equation, c plus d equals 1. Now for the second condition. The derivatives must be equal. We need the left-hand derivative to equal the right-hand derivative at x equals 1. First, let's find the general derivative for each piece of the function. The derivative of x squared is 2x. The derivative of c, x plus d is c. Now we can find the one-sided derivatives at x equals 1. The left-hand derivative is the limit of 2x, as x approaches 1 from the left, which is 2. The right-hand derivative is the limit of c, as x approaches 1 from the right, which is c. For differentiability, these must be equal, so c must be 2. We now have a system of two equations with two variables. Our equations are c plus d equals 1 and c equals 2. Substituting c equals 2 into the first equation gives us 2 plus d equals 1, which means d must be negative 1. Therefore, the function is differentiable at x equals 1 when c equals 2 and d equals negative 1. This ensures the two pieces of the function meet smoothly at x equals 1 with no sharp corner. Let's look at another example to solidify our understanding. Consider the function f of x equals x plus 2 for x greater than or equal to 0, and x squared plus 3x for x less than 0. We need to explain why this function is not differentiable at x equals 0. As before, we'll check the two conditions for differentiability. First, continuity. We need to check if the left-hand limit, right-hand limit, and function value are all equal at x equals 0. The left-hand limit is the limit of x squared plus 3x, which is 0. The right-hand limit is the limit of x plus 2, which is 2. The function's value at 0 is 0 plus 2, which is 2. Notice that the left-hand limit, 0, is not equal to the right-hand limit, 2. This means the overall limit does not exist, and therefore the function is not continuous at x equals 0. Since the function is not continuous at x equals 0, it cannot be differentiable there. We don't even need to check the derivatives. The graph clearly shows a jump discontinuity at x equals 0. The left piece approaches the origin, while the right piece starts at the point 0, 2. This break in the graph makes it impossible to draw a tangent line. This example reinforces the idea that continuity is a necessary, but not sufficient, condition for differentiability. Let's explore another type of non-differentiability. Consider the function f of x equals the cosine of x for x greater than or equal to pi over 2, and the sine of x for x less than pi over 2. We need to explain why this function is not differentiable at x equals pi over 2. First, let's check for continuity at x equals pi over 2. The left-hand limit is the limit of sine x, which is sine of pi over 2, or 1. The right-hand limit is the limit of cosine x, which is cosine of pi over 2, or 0. The function's value at pi over 2 is cosine of pi over 2, which is 0. Since the left-hand limit is 1 and the right-hand limit is 0, the function is not continuous at x equals pi over 2. Therefore, it is not differentiable there. Let's look at the graph to understand this visually. The graph of sine x approaches the point pi over 2, 1 from the left. The graph of cosine x starts at the point pi over 2, 0, and goes to the right. There is a clear jump discontinuity at x equals pi over 2. This example again demonstrates that a function must be continuous to be differentiable. The jump in the graph prevents a single tangent line from being defined. Let's consider one final example, which is a classic IB-style problem. Let f of x be defined as a x squared for x greater than or equal to 2, and x plus b for x less than 2. We need to find the values of a and b that make the function differentiable at x equals 2. We'll follow the same two-step process. First, continuity. For continuity at x equals 2, the left-hand limit, right-hand limit, and function value must be equal. The left-hand limit is the limit of x plus b, which is 2 plus b. The right-hand limit is the limit of ax squared, which is 4a. The function's value at 2 is also 4a. Setting these equal gives us our first equation. 2 plus b equals 4a. Now for the second condition. The derivatives must be equal. We need the left-hand derivative to equal the right-hand derivative at x equals 2. Let's find the general derivative for each piece. The derivative of ax squared is 2ax. The derivative of x plus b is 1. Now we find the one-sided derivatives at x equals 2. The left-hand derivative is the limit of 1, which is 1. The right-hand derivative is the limit of 2ax, which is 4a. For differentiability, these must be equal, so 1 must equal 4a. We now have our system of equations. Our equations are 2 plus b equals 4a, and 1 equals 4a. From the second equation, we can see that a must be 1/4. Substituting this into the first equation gives us 2 plus b equals 1, which means b must be negative 1. So the function is differentiable at x equals 2 when a equals 1/4 and b equals negative 1. This ensures that two pieces of the function join smoothly. Before we conclude, let's briefly touch on a fascinating historical note. In 1872, Karl Weierstrass presented a function that challenged the intuition of mathematicians at the time. It was the first published example of a function that is continuous everywhere but differentiable nowhere. The function is defined as an infinite series involving cosine terms. Its graph is a fractal-like curve that is infinitely jagged at every point. No matter how much you zoom in, it never smooths out, making it impossible to define a tangent line anywhere. This function is a powerful reminder that our visual intuition can sometimes be misleading in the world of calculus, and that rigorous definitions are essential. Let's recap what we've learned today. We started by proving the fundamental theorem that differentiability implies continuity. This means that for a function to have a derivative at a point, its graph must be unbroken at that point. We then showed that the converse is not true. A function can be continuous but not differentiable, as demonstrated by the absolute value function with its sharp corner. Finally, we established a rigorous test for differentiability at a point. The function must be continuous, and its left-hand and right-hand derivatives must exist and be equal. We applied this test to solve problems involving piecewise functions. Understanding this relationship is crucial for higher-level calculus and problem-solving in the IBAAHL curriculum. Thank you for watching. To help you master these concepts, here are 5 practice questions in the style of the IB exam. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1 asks you to find the values of a and b that make a piecewise function differentiable at x equals 1. Question 2 asks you to explain why another piecewise function is not differentiable at x equals 0. Question 3 is a proof that the absolute value of x minus 5 is continuous but not differentiable at x equals 5. Question 4 asks you to find the left-hand and right-hand derivatives of a piecewise function at x equals 1 and determine if it's differentiable. And question 5 asks you to find the derivative of cosine x from first principles, using a given limit. Welcome back. Let's go through the solutions. For question 1, we need to find a and b to make the function differentiable at x equals 1. First, for continuity, the left-hand limit, right-hand limit, and function value must be equal. This gives us the equation a plus b equals 1. Next, for differentiability, the left-hand and right-hand derivatives must be equal. The derivative of x squared is 2x, and the derivative of ax plus b is a. Setting them equal at x equals 1 gives us 2 equals a. Substituting a equals 2 into our continuity equation, we find that b must be negative 1. So a equals 2, and b equals negative 1. Now for question 2. We need to explain why this function is not differentiable at x equals 0. We start by checking for continuity. The left-hand limit is the limit of x squared plus 3x, which is 0. The right-hand limit is the limit of x plus 2, which is 2. Since the left-hand limit does not equal the right-hand limit, the function is not continuous at x equals 0. Because differentiability requires continuity, the function cannot be differentiable at x equals 0. The graph has a jump discontinuity. Let's move on to question 3. We need to prove that the absolute value of x minus 5 is continuous but not differentiable at x equals 5. First, let's write the function as a piecewise function. For continuity, the left-hand limit is the limit of 5 minus x, which is 0. The right-hand limit is the limit of x minus 5, which is also 0. The function's value at 5 is 0. Since all three are equal, the function is continuous at x equals 5. Now for differentiability. The derivative of x minus 5 is 1, and the derivative of 5 minus x is negative 1. The left-hand derivative at 5 is negative 1, and the right-hand derivative is 1. Since they are not equal, the function is not differentiable at x equals 5. Here is the solution to question 4. We need to find the one-sided derivatives at x equals 1 and determine if the function is differentiable. First, let's find the general derivative for each piece. The derivative of negative x squared plus 5x plus 6 is negative 2x plus 5. The derivative of 3x plus 10 is 3. The left-hand derivative at 1 is the limit of 3, which is 3. The right-hand derivative at 1 is the limit of negative 2x plus 5, which is 3. Since the left-hand and right-hand derivatives are both 3, they are equal. However, we must also check for continuity. The left-hand limit is 13, and the right-hand limit is 10. Since they are not equal, the function is not continuous at x equals 1, and therefore not differentiable. So, the left-hand derivative is 3, the right-hand derivative is 3, but the function is not differentiable because it is not continuous. Finally, let's tackle question 5. We need to find the derivative of cosine x from first principles, using the given limit. We start with the definition of the derivative. F prime of x equals the limit of the difference quotient. Now we use the cosine addition formula. Cosine of x plus h is cosine x cosine h minus sine x sine h. Substituting this in gives us cosine x cosine h minus sine x sine h minus cosine x, all over h. We can rearrange the terms and split the fraction. This becomes the limit of cosine x times the quantity cosine h minus 1 over h minus sine x times sine h over h. Using limit laws, we can split this into two separate limits. This gives us cosine x times the limit of cosine h minus 1 over h minus sine x times the limit of sine h over h. We are given that the first limit is 0. The second limit is a standard limit that equals 1. So we have cosine x times 0 minus sine x times 1. This simplifies to negative sine x. Therefore, the derivative of cosine x is negative sine x. This is a classic derivation that demonstrates the power of first principles and trigonometric identities. That concludes our session on differentiability and continuity. I hope this video has provided a clear and rigorous explanation of these essential concepts for your IB Mathematics AAHL studies. Keep practicing, and you'll master them in no time.